All right, everybody. Well, good to see you back. Welcome back to another exciting session of CE 397, Control Theory for Smart Infrastructure. As I mentioned last time, we started our journey into the study of real-time control. We talked about the different types of control. So in particular, active versus passive control. We talked about different control problems and how they relate to civil engineering problems in particular. I gave you some examples of active control problems, such as active control of a reservoir for flood control, active control of a structural response, active control of an HVAC system, be it a building heating system. And I introduced the two major types of active control, the first being open loop control, and the second being feedback or closed loop control. Okay, so we talked a little bit about feedback control. And feedback control essentially consists of a control scheme in which the output of your system is fed back into a controller in order to determine the control signal that will drive your system to a desired state. And I gave you the kind of canonical block diagram for a feedback control system. Let's just go through and label some of these elements here. So we have our plant. So this will represent the transfer function of the physical system that we're trying to represent. We have an input coming into the plant, and that produces our output in the frequency domain, which we call Y of S. And then in the feedback control scheme, we feed back that output. We compare it with a reference. We compare it with a reference signal that we are trying to track. And we subtract our observed output from the reference, which produces an error signal, E of S. And this error signal is fed back into a controller. So this is another transfer function that we are designing to achieve some desired properties of the system. The error signal is fed back into the controller, and that creates our control signal or control input U of S. And that control input is eventually fed back into our transfer function for the system, along with any disturbance inputs coming from outside of the system. So for instance, in a very simple system, the plant might be the thermal equations for a building or a room. The output might be our observed temperature in the room. Our reference is the temperature that we'd like to track. So it's the temperature on our thermostat. We feed that back into a controller, and that produces a heating input that we're going to input into the room to make it achieve our desired temperature. Okay, so that's an example of a feedback control system. And what we saw when we looked at the equations of this feedback control system were that with feedback, we could essentially take our first transfer function corresponding to the system, apply feedback, and that results in another transfer function that we can design. And essentially, we can place the poles of the system where we would like them to be, such that we get the response of the system that we want. And there were a couple advantages of feedback that I alluded to in the last lecture. You'll actually be proving some of these in homework 4. But some advantages of feedback: first, stabilization. So feedback control can take a system that's inherently unstable and make it stable by placing the poles of the system in the left-hand plane. Okay, and we showed how that was possible using kind of just a numerical example. Two other properties of feedback control that are really important. Feedback control achieves both disturbance rejection and reference tracking. So you will actually prove these properties in your homework. But essentially, feedback control, if you design the gains to be sufficient, or if you design the gains of the controller to be large enough, you can essentially reject any disturbances that are coming into the system and make their effect to go to 0. Similarly, by increasing the gains of that controller, you can ensure that you track a reference to arbitrary precision. And finally, one really interesting aspect of feedback control is that it's robust to uncertainty in the system model. This is a really important aspect of feedback control. In particular, this means that you don't need to precisely know your model of the system to get good performance. If you use feedback, even if you don't exactly know all the parameters that characterize your system, it tends to perform very well because you can design that transfer function, that closed loop transfer function, to have the dynamics that you want. Okay, are there any conceptual questions on feedback control before I move on? Any conceptual questions on feedback control before I move on? No? Okay. So towards the end of the class, we moved towards a concrete example of feedback control. And in particular, we started looking at what's called PID control. Does anyone remember what PID stands for? Yeah, so exactly. So it stands for proportional integral derivative control. This is an extremely common control scheme used in industry. We're going to go through how each of those components works, the proportional, the integral, and the derivative components. In particular, we're going to apply it to a real world system. So I motivated this application of PID control in terms of a real world application of PID control, and that is a Segway scooter. So if you've ever wondered how a Segway scooter manages to stabilize itself and stay upright, today you are going to find out. Okay, and towards the end of class, we derived a dynamical model for the equations of motion of the Segway scooter. Essentially, we applied Newton's second law, the angular form of Newton's second law, to derive the equations of motion for this Segway scooter. In particular, applying that Newton's second law, so the rate of change of angular momentum has to equal the sum of moments around the base. We derived this equation of motion that describes the movement of the Segway scooter given some applied input torque from the motor, T of T, along with some applied disturbance force, L times F of T. So sorry, this should be a disturbance moment, L times F of T. Okay, so this here is our disturbance. Okay, some disturbance being applied to the top of the scooter. T of T is our control, exactly. So this is the actuator force, our actuator torque output by the motor. This is what we're trying to control. Okay, so we derived the full equations of motion for the Segway scooter. Unfortunately, what's the problem with this system here? It's nonlinear because of the sine theta t term. So we reasoned that if we're only interested in keeping the scooter upright, such that the angle shouldn't deviate too much from 0, we can use the small angle approximation, and we can write a linearized form of the system like so. Okay, so we have 1/3 m bar. M bar is the mass per unit length times the length cubed times the angular acceleration minus 1/2 m bar, the mass per unit length, times acceleration due to gravity times the length squared times the angle from the center is equal to our applied input torque plus the disturbance moment. So again, this is our control. This is our disturbance. Okay, and essentially, this is the gravitational force. Okay, and this corresponds to the rate of change of angular momentum. Okay, so these are the full equations of motion that describe the motion of the Segway scooter, except that we have linearized them around the vertical position. And this will make it easier to analyze. So the first question we can ask, is the scooter stable without control? Who thinks that it's stable without control? Who thinks that it's going to be unstable without control? Right, most of you. So that you can kind of it's kind of intuitive, right? If you have an inverted pendulum, it's not an inherently stable system. How can we determine mathematically whether the system is stable or not? How do we determine mathematically whether the system is stable or not? Sorry? So we have the differential equation. So that's in our previous slide. What aspect of this differential equation can we look at to determine if it's stable or not? The poles, exactly. So we can look at the poles of the system to determine whether it's stable. So to find the poles, probably the easiest way is to take the Laplace transform of our original system. This will give us the transfer function of the system, and from that we can look at the poles. Okay, so we'll take the Laplace transform of 1/3 m bar L cubed theta double dot t minus 1/2 m bar g L squared times theta t. And then because we don't have control here, we're looking at the system without control, we're just going to set the right-hand side equal to the length times the applied disturbance force. And that's the disturbance moment applied to the top. Okay, so when we apply to the Laplace transform, what does this term here become? Sorry, Laplace transform, not inverse Laplace transform. S squared. Okay, and this just becomes theta s, right? So let's go ahead and apply our Laplace transform. Okay, I'm going to go ahead. Let's just do the full thing. I'll do 1/3 m bar L cubed times s squared theta s minus 1/2 m bar g L squared theta s is equal to L times capital F of s. Okay, what can we do now to simplify this? We want to find the transfer function. Factor out the theta s. Okay, so we'll get theta s times quantity 1/3 m bar L cubed s squared minus 1/2 m bar g L squared is equal to L times F of s. Okay, and so then if we want to find the transfer function, all we need to do is divide theta s by our input on the right-hand side, right? So if we move it over, we have theta s over L times F of s. So for reasons I'll explain later, I'm going to treat the input as L times F of s instead of F of s. It'll just make the presentation simpler later on. So I'm going to treat our input as being this entire quantity, L times F of s. Okay, and this will give us the transfer function 1 over 1/3 m bar L cubed s squared minus 1/2 m bar g L squared. And I'm going to go ahead and monetize this so that this s squared term is monetized. So I'll multiply by 3 over m bar L cubed on the top and bottom. So we'll have 3 over m bar L cubed divided by s squared minus 3g over 2l. Okay, so what are the poles of this system here? What are the poles of this system? Right, exactly. So I'm going to go ahead and write this out again. We have theta s over L times F of s is equal to 3 over m bar L cubed divided by s squared minus 3g over 2l. So if you think back to, algebra, we can factor out this denominator, or we can, factor out the denominator into s minus square root of 3g over 2l times s plus square root of 3g over 2l, right? So this is just applying what you know from algebra 1. all the way back in middle school. And so the poles of the system are plus or minus square root of 3g divided by 2L. So is this stable or is this unstable? Is this stable or unstable? Unstable. Why is it unstable? Exactly. So we have two poles that are along the real number line. One of them is negative and one of them is positive. And we know that if there are any poles on the positive part of the real axis, that system will be unstable. Okay, so we know that without control, our Segway scooter is unstable. Okay, so what I'm going to do now is I'm going to actually go ahead and simulate this system. So if you want to follow along, I have uploaded code. I've uploaded code to Canvas under Files, Code Files, and then I have two files here. I have one called PID in class.ipynb. So that is a Jupyter Python notebook that you can follow along with. I've left some cells blank. So essentially I'll be filling in those cells here, and you can follow along with that example in class. I also have a PID in class.py. And so that's just the same thing, but it's just a Python file. So if you're not comfortable with using Jupyter notebooks, you can use that code. Okay, are there any questions? So this is optional. You don't need to follow along on your own computers, but I would recommend it. Okay. Great. Let me just check something real quick. Am I still on Zoom? I think
yes.
I'm still on Zoom. Okay, Maureen, can you see my screen?
Yep.
Okay, great. Well, I couldn't see the yellow outline, so I wasn't sure if it was still working. Okay, so what we're going to do is we are going to go ahead and run this code example. Okay, so what I've done here is in this first cell, I'm importing NumPy, which is the basic numerical library for Python. I'm importing scipy.signal, which will give us some specific functions for controls specifically. And I'm importing some plotting libraries. Here I'm importing some animation libraries that might be fun to look at later. These won't be in the code file that I gave you just for dependency reasons, but I will use this to make some animations. Okay, so the first thing we're going to do is we're going to set the parameters for the system. So we need to specify the mass per unit length, the length, and the acceleration due to gravity. So I'll set the mass equal to 1. I'll set the length of our pendulum equal to 1.5. And I'll set the acceleration due to gravity to 9.81. Okay, so the way that we're going to simulate this system is we're going to use a built-in function in scipy.signal called transfer function. And I'll just call the documentation. So this is a class for representing transfer functions. It's built right into the scipy library. Note that MATLAB has this exact same function. The one in scipy is just a copy of the MATLAB implementation, essentially. And what we're going to do is we're going to feed this function the coefficients for our numerator and denominator. Okay, so this function here, it takes as its arguments a set of lists. The first list will be the coefficients on the numerator, and the second list will be the coefficients on the denominator of our transfer function. Okay, so let's go ahead and do that. So let's think back to our transfer function. I'm just going to write TF is equal to signal, scipy.signal.transfer function, and I'm going to call it on numerator, denominator. So we have to set the coefficients of the numerator and the denominator of this transfer function. So if we go back and we look at our transfer function for the system, what is going to be the coefficient for the numerator? What's going to be the coefficient for the numerator? So we'll have one coefficient, and it'll be equal to 3 divided by m times L cubed, okay? So in the numerator, we can put 3 divided by m divided by L cubed. Okay, and the denominator, well, first of all, how many places are we going to have? 3, right? We have one for the s squared term, one for the s term, and one for the constant term. Okay, so our first coefficient is going to be 1. Our second coefficient is going to be 0, and our third coefficient is going to be 3g over 2l, okay? So we're going to have our denominator is 1, 0, and negative 3 times g divided by 2 divided by l. I believe it's negative, right? Yes, negative, okay. Okay, so let's go and see what happens when we simulate this system. So what I'm going to do is I have this transfer function here. I'm going to create 2 plots. The first plot will be the output of tf.impulse. What do you think that computes? Based on our knowledge from earlier in the course, there's tf.impulse and tf.step. What do you think those correspond to? Yeah, so it'll be the impulse response and the step response respectively. So the response to an impulsive input first and the response to a step input second. So let's go ahead and simulate the system. And when we plot it, we get something like this. Okay, so we can see here that for this system, the scooter without control is unstable. The angle approaches infinity as time goes to infinity, which means that the scooter is essentially flailing wildly around. I'm going to go ahead and visualize this with this animation here. Let's see what it looks like. Okay, so we have our pendulum, and it just flails wildly around. So, okay, first of all, is this how the actual system is going to behave? No. Why is it doing this? Right. So 2 reasons. One, it doesn't have the boundary conditions corresponding to the ground. What's the second reason? What did we do to our original equations of motion? Yeah, we linearized it. Right. So linear functions can explode to infinity, whereas nonlinear functions often saturate. So just for completeness here, I'm also going to plot the poles of the system. On the x-axis, we have the real component of the pole. On the y-axis, we have the imaginary component of the pole. And you can see that we have 2 poles, one located around -3 and one located around +3. And this positive pole here is causing the system to become unstable. Okay, so what can we do about this situation? Thinking back to last class, how can we stabilize a system like this? How can we stabilize our scooter? Feedback. Exactly. So we can stabilize this scooter using feedback control. So what this would correspond to in the real world would be, we have some sensor that's able to measure the angle, right? That sensor inputs that angle, the measured angle, into some control rule, which is used to create actuator signal that's going to control the scooter position using some motor inside of it, right? So what we want to design here is that control logic. Okay. So perhaps the simplest way, the first thing we might think of, if we want to create a control rule that stabilizes the system, is to simply look at the angle, its deviation from the center, and apply a countervailing force that's proportional to our deviation from the center. That sounds pretty reasonable, right? That is what is called proportional control. Okay, so this is going to be our first attempt to get the system to behave how we want it to get the Segway to work the way it's supposed to. So in proportional control, all we're doing is we're saying that we want the torque applied by the motor. So I'm actually going to call this TP of T. We want the torque applied by the motor to be proportional to the deviation of the angle of the scooter from our reference angle, our desired reference angle, which in this case will be 0. Okay, so we'll define our input torque, our control torque, to be equal to some constant Kp times theta ref of T, so this is our reference angle, minus theta T. Okay. And generally, this will be expressed in the frequency domain. So if we take the Laplace transform, we simply get Tp of S is equal to Kp times theta ref of S minus theta S. Okay, so we're feeding back a control torque that's in direct proportion to the deviation of the scooter's angle from our desired angle. Okay, so that's all we're doing here. Okay, we can draw this out in block diagram form. So let's say we start with some disturbance force F of S. We multiply it by the length of the scooter L to get a moment L times F of S. Okay, that goes into this junction here. And that gets fed into our transfer function, which I'll write as 3 divided by m bar L cubed. So this is just the same transfer function as before, divided by S squared minus 3g over 2L. Okay, so that's the transfer function of the uncontrolled scooter. That'll output our output of the system, which is theta S, okay, our angle in the frequency domain. We're going to take that output. We're going to compare it to our reference angle, which in this case is simply equal to 0. Okay, so we're going to take our reference angle, add it, and subtract our actual observed angle, and we're going to feed it back into a controller. And our controller is just going to be this constant Kp. Okay, so after we feed that error back into our controller, we take the output of the controller and we feed it back as an input to our system. And this is the control torque, which I'll call Tp of S. Okay, and these get summed together at this junction here. Okay, so we're adding the motor torque along with the disturbance torque together, and that will force the system. So let's see what happens when we do that in terms of the mathematics. So we're going to look at the mathematics first, and then we're going to go and simulate it. Okay, so let's see what happens to our closed loop transfer function when we apply this feedback. Okay, so we need an expression for theta S, our output. If we go and we follow this diagram here, we know that theta S is equal to this transfer function times Tp of S plus Lf of S, okay, because that's what's on this incoming branch right here. And Tp of S is simply equal to Kp times negative theta S, right? Because our theta ref is 0. Right. So on this branch here, the error between the reference and the angle is simply equal to negative theta S. Okay, so if we follow that through, the input that's coming into our system transfer function is L times F of S minus Kp times theta S. Okay. So our theta S, our output, is equal to L times F of S minus Kp times theta S, all times H of S, our open loop transfer function. Okay, so let's go ahead and rearrange this. We want to isolate theta S over our input, L times F of S. So we have L times F of S. If we just manipulate this, we get L times F of S times h of s is equal to theta s times quantity 1 plus kp times h of s. And our closed loop transfer function, which I'll write as theta s over L times f of s. This is going to be equal to h of s, our unstable transfer function, over 1 plus kp times h of s. Okay, so this is similar to something we looked at in a previous class. So let's go ahead and compute. Let's expand out h of s to see what the closed loop transfer function looks like. Okay, so we have that h of s is equal to this expression here. It's this open loop transfer function. So let's go ahead and substitute that in. In the numerator, we have 3 divided by m bar L cubed divided by s squared minus 3g over 2l. So this is simply our open loop transfer function in the numerator, divided by 1 plus kp times that same transfer function, 3 divided by m bar L cubed divided by s squared minus 3g divided by 2l. Okay, so as we did before, we can take this 1 here and we can re-express it to have a common denominator with this term. So 1 will equate to s squared minus 3g over 2l divided by s squared minus 3g over 2l, right? And if we do that and we sum them together, we will get the following expression. I'll do this first example in all of the gory detail, and then for the other components of the control, I'll kind of gloss over it a little bit. So I won't do this full derivation for each term of PID control, but I want to do it for this case just to be explicit here. Okay, so we're gonna expand out this term in the denominator. So we have theta s over L times f of s is equal to, okay, we have the same numerator as before, so 3 divided by m bar L cubed divided by s squared minus 3g divided by 2l, all over s squared minus 3g over 2l plus kp times 3 divided by ml cubed, all divided by our original denominator, s squared minus 3g over 2l. Okay, so you can see that this denominator here and this denominator here are going to cancel out. And so the final expression you end up with for our closed loop transfer function is the following. Theta s over L times f of s is equal to 3 divided by m bar L cubed divided by s squared plus quantity kp times 3 divided by ml cubed minus 3g over 2l. Okay, so we have a different transfer function now. It looks a little bit different. When is this system going to be stable? When is this system going to be stable? Let me write this out. When is the system going to be stable? Exactly. So we want the poles to not have a negative real part if we have the following. So the system is stable. Well, actually, I'll put a little asterisk there. System is stable when 3 times kp divided by m bar L cubed is greater than 3g divided by 2l. Okay, so essentially we want this quantity here to be positive. Right? If we had an s squared minus something, then that would give us a root with a positive real part and a root with a negative real part. If we have that this term here is positive, we'll have something else. So we won't have a root with a positive real part. So let's go ahead and see what happens when we implement proportional control like this. Let's see what the response is going to look like. Okay, so I'm going to go ahead and I'm actually going to copy this here. All right. Yeah. All right. So we have that our numerator should be the same, right? Numerator of our transfer function should be the same. It's 3 divided by m bar L cubed. We're going to want to define a control gain. So I'm just going to define it as 14. Just cause. Okay, and then we want our denominator to look like this. So let's go ahead. So our first coefficient will be the same. Our second coefficient will be the same. And for our third coefficient, we will have Kp times 3 divided by m divided by L cubed minus 3g over 2L. So help me remember this here. Kp times 3 divided by m divided by L cubed. Okay, does that look right? All right, let's go ahead and try it. So we now have a proportional control gain being applied to the system. And let's see what happens when we apply our proportional control. Okay, so this is what the response looks like. The top is the response to an impulsive input, and the bottom is a response to a step input. So is the system stable or unstable? It is, what do we call this? What do we call this condition? Yeah, so this is marginally stable, right? Marginally stable. Why did this happen? Why did this happen? So let me go ahead and plot out the animation. So we'll have essentially a pendulum that is oscillating forever. So why did this happen in terms of the poles? Because they're purely imaginary. If we go and we plot out the poles, we'll find that with proportional control, both of the poles will be strictly on the imaginary axis, okay, which means that our Segway scooter is just going to continuously rock back and forth forever. Okay, and this is not ideal. You know, this is not going to be a fun time if we try to ride this, because it's just going to be constantly wobbling back and forth, and we're going to get nausea. So let's think mechanically. What is it that we've created? What is it that we've created here? Maybe if you think back to our structural system, our mass spring damper system, what mechanical device have we effectively created here? A simple harmonic oscillator, or in kind of concrete terms, an undamped spring. So we've created essentially an undamped spring. So if you want to think in shorthand, proportional control essentially adds springiness to your system, right? It's pushing back in direct proportion to your deviation from some reference. So as your angle increases in position, or if the deviation from the reference angle increases, the proportional controller will push back in direct proportion, which will cause it to move back towards the left, where eventually it will get another force pushing it back in the opposite direction. And so you'll end up with this system where you are constantly just oscillating back and forth. So what can we do? If we think mechanically about our structural system, for instance, What can we add to this system to cause those transients to die out? We think back to our structure. We think back to how we simulated in kind of the first couple lectures. What do we need to add to this system, this mass spring damper system, to cause the oscillations to die out? We need to add damping, right? So if we go back to our original transfer function here for proportional control, what term are we missing in the denominator? Yeah, we're missing the S term, which corresponds to the damping. So what we need to do next is effectively create artificial damping to cause those transients to decay down to 0. And we can do that with what is called derivative control, or I'm going to call it, let's call it derivative control. Okay, so with proportional control, actually, let me call this proportional derivative control because derivative is almost never applied just by itself. So we'll do proportional derivative control. So what we're going to do is, instead of just having that proportional feedback, we're going to feed back. What do you think we're going to feed back? Judging by the name. Yeah, we're going to feed back the derivative of our angle minus the derivative of the reference. Okay, so we have our torque, our derivative component of the motor torque is equal to some constant kd times quantity theta ref dot of t. So this is our reference angular velocity minus theta dot of t. So this is our actual angular velocity. Okay, so we're feeding back the difference between those two. We will treat this theta dot ref as 0 in our implementation, just to simplify things. Okay, and in the frequency domain, what will this become? So if we take the Laplace transform, what will this become here? Let's start with this one. What does theta dot of t become in the frequency domain? S times theta s, right? Okay, and this becomes S times theta ref of s. Okay, so in the frequency domain, our proportional derivative controller will be equal to S times kd times theta ref of s minus theta of s. Okay, let's draw the block diagram again. Okay, so we have our input disturbance force F of s being multiplied by the length of the pendulum. That gives us our input moment disturbance L times F of s. Okay, that gets fed into our transfer function. I'm just going to write it as H of s. Okay, that produces some output theta s. We're going to take that output. We're going to compare it to theta ref of s, which is going to be equal to 0. And we're going to feed that difference into a new controller, which will be, in this case, equal to Kp, our proportional control, plus, what do you think the other component will be? SKD. Very good. Okay, so we're, by multiplying our error by Kp plus SKD, we're feeding back both the difference in the angular displacement as well as the difference in the angular velocity, and we're adding them together. Okay, so that we're going to take and we're going to feed back into our system, and we will see what the response will become when we do that. Okay, so I'm not going to go through the full detail again, because the process is almost the same as for proportional control, but here's how we can compute the closed loop transfer function. We have theta s we follow those links on the block diagram, we will end up with theta s is equal to L times f of s minus Kp plus skd all times theta s all times h of s. Okay, and if we divide through and find our transfer function, our closed loop transfer function, theta s divided by L times f of s, we will get h of s divided by 1 plus Kp plus skd times quantity h of s. And I'm not going to go through the full detail of how to do the algebraic manipulation again, but what you will end up with in terms of your closed loop transfer function is 3 divided by m bar L cubed divided by s squared plus quantity kd times 3 divided by m bar L cubed times s plus quantity Kp times 3 divided by m bar L cubed minus 3g over 2L. So that corresponds to the gravitational force. Okay. So here we have the equation for our, essentially for our structural system or for our mass spring damper system, where the proportional component corresponds to essentially as we increase Kp, that increases the stiffness of the system or the springiness of the system. And the derivative component here, as we increase the derivative gain, that corresponds to increasing the damping of the system. Okay, so we can, if we increase this KD coefficient sufficiently, we can cause those oscillations to die down to 0. Let's go ahead and simulate this as well. Okay, so I'm going to go and copy this here. And let me just figure out what coefficients I want to use here. All right. So we're going to have something very similar. Let's set Kp is equal to 20. Let's set Kd is equal to 1. These are kind of just arbitrary here. And for our transfer function, we now need to add in this term for the s place. And what was our expression here again? Kd times 3 divided by ml cubed. So this will be Kd times 3 divided by m divided by L cubed. So let's go ahead and see what happens when we simulate this system. And here is our impulse response and our step response. Okay, so it looks almost exactly the same as the structural system that we looked at earlier in the class. You see that the when it gets hit with an impulse, the angle initially increases rapidly. It restores its position, and then that damping causes the oscillations to eventually die down to 0. Okay, and we can go and we can simulate the animation as well, just to see what it looks like. Okay, so essentially the pendulum gets hit with an initial disturbance, but it eventually corrects itself to the reference angle. Okay, so this is very similar to our mass spring damper system. Okay. Are there any questions on anything I've covered so far before we move on? Any questions about PID control? Yes. So typically when you're doing control problems like this, you would just treat your initial conditions as being like an impulsive input occurring at time 0. Essentially, it's the two are equivalent. And when you're simulating a system like this, you can also input the initial conditions if you want. When we're computing those closed loop transfer functions, though, we're just computing it with respect to an arbitrary input. and your initial conditions can be thought of as a type of input occurring at time 0. Okay. And I can show you how you can include initial conditions for these simulations as well. Okay, so we got a much better control response this time. It's doing essentially what we wanted it to do, but there's one problem. So if we look at the step response, what is the step response doing? So first of all, what does the impulse response and step response correspond to respectively, like in just intuitive physical terms? Does anyone want to answer or venture an answer here? This is just an intuitive question. So what does the impulse response correspond to doing to the Segway scooter? Just like hitting it or something, right? Or just giving it a shove. What does the step response correspond to? Yeah, you're like leaning on it. So one thing to note here is that for the step response, you get that the system responds initially. Okay, so the angle increases and eventually that angle dies down, but you'll notice that we're no longer at our reference angle. Okay, so there's a constant offset between our actual angle of the scooter and our desired reference angle that we wanted. Okay, so there's one more component of PID control that we can use to address this problem, and that is integral control. So let's introduce integral control. Okay, essentially what we're going to be doing with integral control, I'll write it out mathematically first. Okay, we're going to be applying another torque. I'll call this Ti of t. And it's going to be equal to some constant Ki times the integral from 0 to t of theta rep tau minus theta tau d tau. Okay, and in frequency domain, what will this become? So first of all, what will this expression here become in the frequency domain? This is relevant to homework 3. What is it, how do we, if we take the Laplace transform of an integral, what does it turn into? Yes. So it'll be, we'll end up with 1 over s times ki times quantity theta rep of s minus theta s. It's equal to Ti of s. Okay, so what is this actually doing? This is kind of a bit more abstract than the other two. What is integral control doing? And why would it help eliminate steady state error? Maybe I can give some physical intuition for what's going on here. If we think of our system like a spring mass damper system, let's say we have some spring. That was not my best spring drawing. We have a damper. Maybe we have some sort of handle. And let's say we pull on this spring damper system with some constant force. So I told you that the proportional control is like a spring. So as we take this spring damper system and we pull on it with a constant force, that spring will pull back with some constant force equal or proportional to the force that we're pulling on it with, right? So if we take this spring system, we pull on it with a constant force, as we're holding it, the spring will pull back with some constant force, right? But it may not ever return the the mass or the spring that we're holding to its original position, right? It's just pulling back with some constant force. It's not guaranteed to pull our spring back to its original position. The damper, well, the damper only exerts a force when we're yanking on it. So when we're yanking on it, it'll pull back with a force that's proportional to the velocity that we pulled on the damper with. Okay, but if we're just holding it, it won't apply any force at all. So what the integral controller is doing essentially is that if we take this spring mass system and we pull on it, the integral controller will pull back with a force that's proportional to essentially how long we have held the spring out for. Okay, so the longer we hold that spring out for and the longer we cause the spring to deviate from its resting position, the harder that controller will pull back. So what that ultimate effect is to cause the system to go back to its reference position. Okay, so essentially the integral controller is, if we're holding it away from its reference position, it will pull back harder the longer that we have held it away from its reference position. Okay, and that's what causes that steady state error to decay to 0. Okay, so just as before, we can write out the equation for the closed loop transfer function with PID control. I'm not going to do this full thing in detail again. Essentially, all I'm going to do at this point is show PID control and then just talk a little bit generally about controls and some things to think about when you're doing controls. And I might give you a chance to do some experiments on your own if we have time. So the closed loop transfer function will be equal to, if we follow those loops on the block diagram, we'll get L times f of s minus Kp plus skd plus 1 over ski all times theta s all times h of s. Okay, and if we write out our transfer function theta s over L times f of s, what we will eventually end up with is following expression. So in the numerator, it's still going to be the same, 3 divided by m bar L cubed divided by s squared plus kd times 3 divided by m bar L cubed all times s plus the proportional term Kp 3 divided by m bar L cubed minus 3g divided by 2L. And then we have this additional term, an additional term, 1 over s times, I don't know if I'm going to have room here, but it'll be Ki times 3 divided by ml cubed, or m bar L cubed. Yikes, don't have enough room there. Okay, so what we can do to make this more familiar and more amenable to analysis is we can multiply both the numerator and denominator by s. Okay, and that will give us 3 divided by m bar L cubed times s divided by s cubed plus kd times 3 divided by m bar L cubed times s squared plus Kp 3 over m bar L cubed. I'm just going to write this whole thing out. Minus 3g over 2L times s plus Ki times 3 divided by ml cubed. Sorry, m bar L cubed. Okay, so one thing to note here, what have we added to this system that we haven't had before? Sorry? So what's in the numerator now? We have a 0 in the numerator. Okay, so this is the first time that we're dealing with a 0 in the system. And we also now have a third order system, which we haven't dealt with before either. Okay, so let's go ahead and simulate this system. see what it looks like. Okay, so we have proportional integral derivative control. I'm just going to copy from here. And I got to decide on my control gains really quick so it's not unstable. All right. So I'll set KP to 20. I'll set KD to 20. And I'll set KI to 0.5. Okay, so our numerator, we now have a 0. So our numerator will have 2 components in this list. We'll have our first coefficient, and then our second coefficient will just be 0. The bottom should be the same, except we now have an additional term, which will be Ki times 3 divided by m bar divided by L cubed, if I am remembering this correctly. Yes. And then everything else will be the same. So let's cross our fingers and simulate it here and see what we get. All right. And so this is the response of the system with PID control. It looks a little bit different than before, but you can see on this bottom plot for the step response, we now have that the error between our angle and our reference angle eventually decays to 0, which is what we wanted. Okay. And let's go ahead and just plot the animation to see what it looks like. We'll see that in this case, the system just very quickly is able to restore itself to its original position. And also there aren't really any oscillations either, which is nice. So that is PID control. Each of the parts of PID control performs its own function, and each one of them are important. So just to recap, what are the different components of PID control doing? So first of all, what is proportional control doing? Let's just think about the different functions of each of them. Okay. Okay, so our P term, what did we use? Why did we put in the P term in the first place? Remember? Yeah, to stabilize the system. So our P term stabilized the system. And it essentially applies springiness, or it makes the system act like a spring. So it applies, I'll just write springiness. Okay, what was our D term for? What was our derivative term for? Yeah, so it applied damping. Applies damping. Okay, and we use this to let's see, how should I word this? To reduce transients, or to cause transients to die down. And finally, what was our integral term for? Why did we apply the integral term? Reduce what type of error? Steady state error. Okay, so the I term reduces steady state error. Okay, very good. One thing I want to note, when you're applying PID control, especially for the integral component of the control, you have to be careful not to destabilize the system. So integrating that error over time can lead to destabilization of the system. One way you can look at this is by looking at what's called the root locus, which is how the poles move through the complex plane as you change those control gains. Okay, so for proportional control, we're moving from dark to bright here. So initially our poles started off on the real axis, and as we increased that proportional gain, they moved towards the imaginary axis and then eventually moved up the imaginary axis and down the imaginary axis. That is the effect of the proportional control. With PID control, with PD control, the story is much the same, except that instead of landing on the imaginary axis, they start moving into the negative side of the real number line, okay, which causes those transients to die down. For PI control, this is sometimes used, but it can be dangerous. For PI control, we have that our poles initially start in these three locations here, but applying the integral gain actually causes it to, it can become more unstable. So you have this pole here that will eventually move into the right-hand plane. So it was already unstable to begin with, but if you apply PI control or the integral portion of the control, it can sometimes destabilize your system. And finally, here's what the root locus looks for PID control. I kind of got this interesting pattern here where your poles are moving in kind of these circle patterns. Okay, so this is one way to analyze how your system is going to behave as you increase or decrease these gains. And a lot of the art of control comes from trying to figure out how to place the gains for each of these terms, specifically for PID control. So one final thing I want to do before we get out is I want to talk about the limitations of PID control. So let's talk about limitations of PID control. Okay, so we saw that PID control is great for a lot of things. It's great at achieving stabilization. It's great at reference tracking, and it's great at disturbance rejection. What are some types of control problems that PID won't be able to handle? So what is PID control? What would it not be good for? What kind of real world control problems can you think of that PID controller wouldn't work well for? Can you think of any applications where PID wouldn't really do a good job? Would it not work on anything that isn't the second order? So it'll work on higher order systems as well, and it will work on first order systems, although the D term won't really be important there. P control will generally work by itself. What I want to kind of emphasize is that PID control is fundamentally reactive. It's fundamentally a reactive control paradigm. Okay, and that the control that is being applied to the system just depends on the current state of the system and its derivatives and integrals over time. What it doesn't perform particularly well for is systems with limited actuator authority. And I'll talk about what that means in a second. So I'll write, has problems when actuator authority is limited. Okay, so let's say you're a flood control operator, so you're operating a dam, and you want to release water from the dam to make sure that the system doesn't flood. PID control won't perform particularly well here because your control strategy only has access to the current state of the reservoir. So for instance, its depth and its derivatives and integrals over time. So for a problem like reservoir control, what you really need is a prediction of how the system is going to behave, because you can only let out so much water at a time, right? If you base your control just on the current state of the system, you may end up with a situation where a large flood wave comes in and you aren't able to let out enough water to prevent it from flooding. So PID control is not particularly good for situations where you have limited actuator authority, which happens to occur a lot. Especially in civil engineering systems when you're dealing with these systems that have huge amounts of inertia. So for situations like that, like for the flood control problem, what you'll want to use is a predictive control strategy. And towards the very end of class, we'll be talking about probably the most popular predictive control paradigm, which is model predictive control. And that will occur much later in class, but I just want you to note that there are different control paradigms. PID is not the only game in town. It is just a particularly effective control strategy for many problems that will crop up in a practical sense. Okay, and with that, I am out of time. So again, I will be holding office hours after the EWRE seminar at 4:30. So please come talk to me up in ACJ 8th floor if you have any questions. And with that, have a nice weekend.